Yes.
Awesome. Okay.
Let's see.
All righty, everyone. Welcome back to the morning session. I'm Karen Kinamuchi, and I'm the moderator for this short session. Our first speaker for this session is Laszlo Molnar, and he'll be talking to us about space missions, specifically Kepler, TESS, and Gaia. And Laszlo, I'll interrupt you at the 17-minute mark.
All right. Thank you. Hello, everyone. I'm Laszlo Molnar from Concordia Observatory. So same place as Robert. And I'm very glad that I've been invited to this lovely event. And I will continue where Robert has left off and talk about how space missions evolved after Kepler, starting with the K2 mission, which was, of course, the repurposed Kepler Space Telescope that operated from 2014 to 2018. I will talk about some first results from TESS, and then I will show a few slides about what Gaia can offer for IRL arrays. Is my animation playing? I think I can't see the screen, but I think my presentation is stuck at the first slide.
Yes.
All right. Yeah. Let's try this again. No, it's still not changing the slides. All right. I will switch to the PDF then. It sometimes happens with Keynote, unfortunately. Let me just share the PDF version. There we go. I'm back in a second. Let's see. Yeah, there it is. Yeah, so this means no animations, unfortunately, but at least the slides are going. So first, I want to talk about K2, which was, of course, the new mission given to Kepler after the reaction wheels failed. And it covered, at the end, 20 plus 1 fields along the ecliptic. And here on this plot, I'm showing all the RL areas that were targeted. And with K2, we were able to go 2 orders of magnitudes higher in the number of proposed RL arrays compared to the original mission. So in Kepler, I think about 40 to 50 stars were observed. And in the K2 mission, we proposed over 4,000, which was a huge success. But of course, because K2 had its inherent problems with the telescope jiggling back and forth a little, they presented new difficulties in processing the photometry. So that's one reason why you probably haven't seen too many K2 results in the literature so far. There have been a few papers out already. At the start, we presented 2 results. First, from the very first data set, the first 9 days of engineering data, we pulled out the light curves and showed that Kepler still works and is able to give high precision photometry for RL arrays. And then we looked at a small dwarf galaxy next to the Milky Way that included 3 RL stars. These are 21 to 22 magnitudes faint, and we were still able to get reasonably good photometry for them. And I am only showing here 2, and the lower one is, I think, the farthest star where we have resolved Blasco effect with the period that we could determine. I think that is one of the few stars beyond the Magellanic Clouds where we actually see the Blasco effect happening in an acceleratic RRD star, RRAB star. So that was a very neat little result. There were some more results. Don Course published a paper about a triple mode RRD star. Now we know that it's not that unique actually. It's just an RRD star with one of these abundant additional modes in it. And thinking back of Gergely's presentation from yesterday about binary RRC stars, there are a number of binary RR LIDAR stars. There are a number of RRC stars that show strong phase modulation. And one of them was observed by the K2 mission. But if you calculate the required mass, it turns out that you need an 8 solar mass black hole for this RRC star to orbit to cause this strong phase modulation, which I think we can pretty much rule out based on statistical grounds, because of course you should need to see a lot more in RRAB stars that do the same because they're inherently more abundant, but we are not seeing that. So it's probably not another light orbiting a black hole, but rather some other effect that causes the RRC stars to show strong phase modulation. Now, the problem with K2, as I mentioned, is that getting really high quality light curves out can be difficult. There are a number of ways to process K2 observations, but those mostly focused on solar-like stars, exoplanet hosts, so stars with small amplitudes, low-level variation, not really well suited for RLI stars with fast and large variations. So we developed our own system where we select the pixel apertures, then separate the astrophysical signals and the systematics coming from the movement of the telescope. We first did this manually, and we managed to do it for 400 stars from the first, from campaigns 3 and 4 and 5. But of course, this wasn't really feasible to upscale it to thousands. So we put in more work and more thinking, and then managed to automatize this process. And we have recently released nearly 4,000 light curves, covering campaigns 5 to 19, except for the 2 batch fields that were 9 and 11. And very briefly, this process automatically selects the right pixels that contain the RL light rate through an iterative process. That gives us a raw light curve that we post-process with one of the systematic corrections tool called K2SC. And then we run it through our own trend removal post-process, which is basically a polynomial fit, which we optimize by forcing it to minimize the phase dispersion of the light curve. It looks something like this. This is not an RLI. It works for a number of different variables as well. And the difference here is the black curve is if we naively fit a polynomial to the light curve, and you can see as it reaches the edges, it tends to curve towards the end of the light curve. If we force basically the cycles to line up, so we determine a period, and then we force the cycles to line up, this will create a much better fit. And this way we can remove even worse trends from these light curves. So there's more to come from K2. There are a number of papers underway. There is an RRD paper being written by Jim Nemec and Pavel Moskalik. This has been in preparation for a while, so it will hopefully come out very soon. The Concoy team is working on a number of topics. We are finishing a paper on RRC stars, and in this plot you can actually see a number of Blasco RRC stars from the K2 campaigns. and this is just a subset of them. You can see there are a number of different shapes and amplitudes and periods for the Blasco effect in RRC stars. And we see them very nicely with K2 because the periods are pretty short. We are also started to work on the RAB stars. There's a lot of more of them, of course. We are going through the detection of additional modes and classification of additional modes. And as Robert mentioned, we are also looking into how the phase and amplitude modulation is related to each other in the stars and how they change over time, change compared to each other. So we only just started this work. We might be able to show some first results in the La Palma conference in a few months. And there is also a very interesting modeling paper coming up, trying to explain the 0.61 modes in RST stars. So keep an eye out for these papers. Unfortunately, I cannot show you this animation. It should show how stars can be detected in globular clusters. And this is differential image, so RLI stars should be blinking in the video. The main point is that K2 observed a number of globular clusters, 8, I think. And although you wouldn't think that Kepler with its low resolution is any good for globular clusters, we can actually get out photometry for RLI stars from those clusters. Of course, if you are at the edge of the cluster, like in the lower panel here, which is V1 in NGC 5897, the glide curve is crystal clear, matching what we can observe in field stars. If you are in the middle, for example, in V13, the quality drops considerably, but still it's a continuous light curve, which can be analyzed pretty thoroughly. For example, you can see here that this star is actually a modulated RRC star. And this is work being done by one of my students, and she's planning on presenting this in La Palma as well. Switching to Gaia briefly, because then I will talk about how we can combine Gaia and TESS. Gaia and DR2 has been the largest hole of RLI candidates so far. I think Igor mentioned this yesterday, that only Gaia is exceeding the numbers that the Augur survey produced. In DR2, 2 classifiers have been run on the data, which produced more than almost 230,000 candidates in total. One of these classifiers was a general classifier that only looked for identifications, and those stars in the Vari classifier result table have no detailed properties. I think it doesn't even have periods, only identifications. The specific object studies was a lot more detailed. This was organized by Gisela Clementini, and that observed or detected 140,000 RLI rays, and there we have periods, there we have Fourier parameters. We even have photometric metallicities for a subset of those. And of course, there is a large overlap between these 2 classifiers. And of course, Gaia is a photometric mission, so we can put all the detections and brightnesses and everything on a map. So if you just plot all these 230,000 stars on a map, you can nicely see a lot of galactic structure. You can see the high density of stars in the bulge, and then you can see the Sagittarius dwarf sticking out to the south from the bulge, and the 2 Magellanic clouds. And then RLI is dispersed throughout the halo. What is important to know about Gaia is that it's photometric mission, so the parallax accuracy actually scales with apparent brightness with the stars, or at least scales more with brightness than with actual distance. So you can measure the parallax of a brighter star and a farther distance than a faint star closer to us. So that basically gives us a practical magnitude limit where the distances and parallaxes start to become very uncertain. And this was tested by the Pan-STARRS team. They compared both the Baylor-Jones distances and the parallaxes to their own statistical parallax for RL-Iris. Since RL-Iris are basically pretty much standard candles, we can do this comparison. And one important thing to note here is that the main reason we have the Baylor-Jones distances is that it's not the best technique to just invert Gaia parallaxes, because they are not exactly just a number. They are distribution of observations and then distribution of individual data points. There are statistical difficulties or statistical finer points how to invert a set of observations. And so that was one thing that Baylor-Jones papers have done. The other thing is putting a galaxy prior in it. So if you have a parallax very close to zero, you won't put your star at infinite distance, but you force it into some galactic population with reasonable distances. Now, the downside of this technique is that if you just naively took these distances, if your star is too far out, you're basically only seeing where most stars in the model are. And this is what is shown here on the left plot. So for about 5 to 8 kiloparsec, the parallaxes, the distances from Pan-STARRS and the Baylor-Jones catalog line up. And then after about 8 kiloparsec, we lose the parallax information. And then the galactic prior takes over and just forces every star into this 5 to 10 kiloparsec range. So that gives us a practical limit to where geometric parallax is useful in Gaia. And on the right plot, you can see the same, basically, that beyond 5, 8 kiloparsec, basically you use any precision and parallax values are all over the plot. This will slightly improve. These have slightly improved in EDR3, but of course, not by a large amount. I can also give you a preview for DR3 because these numbers have already been published. There will be a large increase in the number of RLI candidates. The specific object studies pipeline found 270,000 stars. And with the general classifiers, we are nearing 300,000 RLI candidates in DR3 coming out on Monday. Of these, 134,000 will have photometric metallicity calculated, and 140,000 will have absorption coefficients calculated for the Gaia passbands. And the data set I'm most excited for are the RV time series, because they will release a subset of RV time series for a relatively small number of stars. This means 1,100 RL-Iris and about 800 Cepheids, which doesn't seem much compared to the 300,000, but it is still a lot more than we have detailed RV curves right now. And so I think these data sets with photometry and RV data taken simultaneously by Gaia will be a fantastic new resource. And I'm moving on to TESS. Here I want to talk about our first light paper. I think pretty much the first and only detailed RLI paper so far from TESS. It took a while to work through all the little details, but we at the end published the detailed analysis of 126 bright RL-Iris from the first 2 sectors. These also include the area of the Magellanic Clouds, and because of that and the low resolution of Kepler test, we had to do our own photometry. We made a differential image photometry for each of the stars. Here you can see the comparison. The upper row is a halo star. So if you remove all the background, it reveals the variable source very clearly, but you can see how much lower the resolution of the whole image is compared to the DSS image. The lower plot is near one of the Magellanic Clouds, and you can see that a lot of stellar residuals are present on the image, but we can still pick out the Aralaria star in the middle. Then we classify the light curves via relative Fourier parameters, just the same way as the Ogle team and many others do. But of course, there still can be uncertain in some cases, because you can have light curves that are superficially similar to Aralaris. All right, I will speed up. I quickly put this plot in because there was a question about it. We do see a few non-modulated stars that have shown no signs of modulation, but it's very difficult to really decide. And of course, 27 days is not really enough to be sure. I will skip that. We use Gaia data to really check the absolute brightnesses of the stars, because we managed to find one star that has been classified as a binary candidate Aralaria 3 years ago, but the test light curves show that it's actually an eclipsing binary. And if we combine TESS and Gaia, we can put these stars on period luminosity diagrams and color magnitude diagrams. This is important because we can now do this not for a subset of stars, for a globular cluster, for example, where we have distance data, but we can take a random sample of stars and just put them on the same figure at nearly the same precision. And now that we have these stars in the color magnitude diagram, we can also look at their light curve properties in more detail and look for additional modes in them. And that's what Robert alluded to. We can pick out these millimagnitude modes, but it's difficult to work them because you have the radial mode in there, so you have these combinations. But in RIB stars, we see this wide spread of modes, which we are not really sure about where they come from. What the lower sequence might be the second overtone, but we need models to confirm that. And where I want to get is the RRC stars, where we see a lot of signals. We also see a difference between the bulge and the halo stars that hints at some differences because the metallicities of the bulge and globular clusters and halo stars is different. There is a hypothesis for these stars that they might be high L degree non-radial modes, 8th, 9th, or even 10th order modes, which seems weird, but we can now actually test this hypothesis. And I might run 1 or 2 minutes over my time here, but I think this is very exciting. Now we can select fierce stars, compare their color and absolute brightness and their test frequency data, and we can test how their modes are excited. And what we find is that these modes mostly appear toward the middle or the redder side of the overtone stars, and we see pure RRC positors only at the blue edge. And we don't only see this in tests, we also see it in globular clusters where we have enough data, and we also see it in the K2 sample. And with the modeling paper that's coming out is actually finding the same, that the modes are not linearly excited at the blue edge. So we are pretty close to actually confirming these modes being these high M modes. So what we have learned so far that with Gaia and test, we can have a clean and complete sample of our arrays. We can even do a blind search, and we can find a treasure trove of millimagnitude level modes with these missions. And we are now seeing clear signs of internal physics driving the mode selection here. We see both metallicity dependence and temperature dependence. And we can extend this to thousands of arrays or Cepheids. And we now need models to back these observations up. Thank you very much for your attention.
So we have time for maybe one question. Are there any questions? None on the chat. Any in here? Okay, none. So let's thank Laszlo again. Thank you, Laszlo.
Thank you.